Hey everyone, and welcome to another explainer. If you're a focused learner trying to wrap your head around how the industrial world is being completely rewired from the ground up, well, you are in the exact right place. Today, we're unpacking a massive tectonic shift in how we maintain the world's most complex factories. We're going to dive deep into how predictive maintenance is evolving into an absolute AI-driven superpower. We're talking about using incredible technology to literally predict the unseen and stop failure before it even starts. So let's get into it.
To really understand why this is such a game changer, we have to look at the sheer mind-boggling scale of the problem. Fortune Global 500 companies are currently losing a staggering $1.4 trillion a year to unplanned equipment downtime. That's a trillion with a T. That represents about 11% of their total revenue simply evaporating into thin air, just because machines break down when we aren't expecting them to. But let's zoom way in, from that global macro scale down to the absolute micro scale, because the stakes get even higher on the factory floor. Think about aseptic clean rooms. These are the ultra-pure environments where pharmaceuticals and sterile products are made. In these spaces, a tiny, unseen failure, like a microscopic hydraulic leak, can contaminate a single sterile batch. And that one invisible failure instantly costs the facility up to $2 million. This isn't just about a machine stopping for a few hours. We're talking compromised sterility, completely lost product, and massive regulatory headaches.
Section 1. The break-fix disaster. So think about the traditional break-fix model we've relied on forever. You run a piece of equipment until it breaks, and then you fix it. It's honestly like waiting for your car's engine to literally fall out onto the highway before deciding you might, need an oil change. It just doesn't work anymore. Especially when the global average cost of unplanned downtime is sitting at roughly $260,000 per hour. The margins for error are entirely gone. We desperately need a new way of doing things. Section 2. Anatomy of a living replica. When people hear the term digital model, they usually picture a static 3D CAD drawing, just kind of frozen in time on a screen. But a digital twin is something entirely different. It is a living computational mirror. It ages, it learns, and it degrades exactly in step with the actual physical machine sitting on the plant floor. Building that living replica requires a layered architecture. It's a bit like a giant puzzle. First up, you have the sensing layer. That's continuous telemetry pouring in from IoT particle counters, pressure sensors, and vibration monitors. Second is simulation, where physics-based fluid dynamic models recreate exactly how the machine should be acting. Third is learning, where AI steps in to forecast risk ahead of time. And finally, feedback, where real-world maintenance outcomes actually loop back into the model to continuously sharpen its accuracy. Now, you might be wondering, how do they stay perfectly in sync? This microsecond synchronization relies on ultra-reliable low-latency networks. Today, that means 5G URLLC with roughly 1 millisecond latency, and soon we're looking at 6G HRLLC. And to bridge the gap between perfect virtual physics and the, messy real world, engineers are using advanced techniques like Wasserstein generative adversarial networks. Just think of this AI as a real-time translator between perfect digital physics and messy real-world vibrations. It perfectly matches the digital twin's behavior to the actual physical asset's real-world operational noise. Section 3. Predicting the unseen failure. The defining advantage of having this twin is being able to stress test incredibly dangerous scenarios without ever touching the actual physical facility. You can literally ask the twin, hey, what happens if an airlock is held open twice as long during a shift change? Or what if we throttle an air handling unit? You can safely simulate a catastrophic airflow disruption or a severe humidity spike in the virtual world to see exactly how the equipment will handle it, completely eliminating the real-world risk. To achieve this crazy level of precision, the digital twin runs a seriously heavy-hitting AI stack. But how does it actually predict the future? Well, convolutional neural networks, or CNNs, scan incoming telemetry looking for visual anomalies in the data waves. At the exact same time, bidirectional LSTMs act like a long-term memory, comparing what's happening right now to historical wear and tear patterns over months of operation. Working together with attention mechanisms and random forest classifiers, they don't just detect some generic anomaly. They isolate exact microscopic fatigue signatures. This stack can instantly distinguish between a worn crankshaft bearing and a leaking plunger seal, long before the system gets compromised and shuts down. And the real-world impact of this AI stack?
It is just mind-blowing. In documented cases, these digital twins are predicting hydraulic pump failures up to 8 days in advance with an incredible 87% accuracy. By catching these microscopic faults early, facilities are slashing their unplanned downtime by about 62%.
Section 4. Automating the fix.
But here's the catch. Knowing a failure is going to happen next Thursday is entirely useless if nobody acts on it immediately, right? The absolutely crucial point is execution. If a predictive system just spits out raw data alerts for a technician to manually interpret, sustained adoption drops to a dismal 20 to 30%. But if the system automatically converts a 75% failure probability directly into a pre-populated work order, complete with parts and assignments, sustained operator adoption skyrockets to 85%. Automation is the bridge between that predictive insight and actual physical labor.
Because of this automated, proactive discipline, the financial wins are massive. Facilities aren't waiting years to see if this technology actually works. Typically, companies are yielding an initial return on their investment in just 3 to 6 months.
And look, we are far past the vendor hype phase here. 92% of companies rolling this out report positive returns above 10%, with half seeing returns of 20% or more. There's even a fully documented case of a hydraulic asset deployment that paid back an €840,000 investment in a mere 11 months. That is purely off the strength of predicting failures and stopping them in their tracks.
Section 5. The self-healing future.
So, where is this all heading? We are rapidly moving toward autonomous, self-healing systems, and major players are already putting this into practice. Mitsubishi Hitachi Power Systems has publicly described building the world's first self-healing power plant. They are using reinforcement learning and Markov decision processes to let machines choose their own corrective actions and literally heal their own parameters in real time. No way, right? It's happening.
It all boils down to one absolutely crucial realization. Every sensor stream captured, every fault mode isolated, and every work order automated in the digital twins being built right now is exactly the foundational training data required to achieve tomorrow's autonomous smart factories. You simply cannot skip a step. Which leaves us with a pretty wild thought to chew on. We are entering an era of zero downtime industrial ecosystems. As factories learn to autonomously predict and heal their own unseen microscopic wounds, how long will it really be before machines completely take over their own maintenance? It's a fascinating, maybe slightly intimidating reality that is approaching much faster than most realize. Thank you so much for exploring this with me today in this explainer, and keep learning.